Hello, in this video we are going to go over the notes and talk through what you saw in the pre-lecture video, and then there will be additional videos to get into the problem solving. So on the screen you see the goals of our lesson on exponentials. So we want to be able to write the functions. We practiced that some on our previous lesson. We want to be able to use a calculator to evaluate the functions, so knowing how to type them into our calculator is key. And then we do want to solve them for time, and we can do that either using a logarithm or a graph. I am going to put emphasis on using a graph, specifically Desmos, to do that here in class. However, you may use a logarithm instead if you are more comfortable with that option. So we are actually starting the very end of your pre-lecture, looking at the motivation for this lesson before we actually get into the lesson. So you watched a video that talked about the concentration of a medication within one's body and how that functions. So in this video, we have this curve, and in the first half of the curve, so I'm right here, I'll put a little star here so you know where I'm talking about. There is more drug in, so the curve is going up because the concentration, which is the vertical axis, is increasing. This section is controlled by how the medication is administered. So if you give a medication orally, it takes some time for that medication to work its way through the digestive system and be distributed into the body. And that's the curve that is shown here. It almost looks like a bell curve, though not quite, because we know the bell curve is asymptotic. This one is not. It starts truly at 0, 0. We also know that the bell curve is symmetrical, and this one is not. It goes up more quickly than what it comes down. And so we are going to focus our attention on the second half, the part of the curve that says more drug out. So this part is our focus. And this part is exponential. And we have a couple reasons why this would be exponential in nature. So the first reason why is that it is a curve. And we talked about last week that if it was linear, it would be a straight line, and it's not. So the curve of it is exponential. We also talked about that exponentials have a constant percent. And so in here, we talked about the half-life. So you see there's half the maximum concentration. You see right in the middle here, half-life. And so the half-life is constant. And the half-life, that idea of half, is a constant percent. That is the 50%. And so we talked about last week that when you have that constant percent change, that is when you have an exponential curve. So some really important things that we're going to see in healthcare is we almost always see this idea of the maximum concentration, how much of the med gets to your body. So some things that you take orally, some is digested and excreted before it ever actually gets into your bloodstream and has an impact. And so we have different maximum concentrations than the dosage for some particular meds. And then this idea, I already put an asterisk by it, of the half-life. So over here I put a definition, and that definition is important, that the half-life is the time that it takes to remove half of the drug from the body. And that half-life is constant, and so that 50% is one of the constants that we have. Similar to the normal curve then is sort of the shape of this curve, and it's also the idea here that the total exposure is all the area under the curve. And so we won't use this particular drawing a lot, but I felt like this particular drawing was really helpful in understanding the quantities that we will use frequently. So let's go out and look at a package insert. So this is the package insert for row 7. And we have a pediatric table, and then we have an average adult table. So we're going to look right here at the pediatric table first. And first thing I see is that maximum plasma concentrations. And so I see the two different common dosages for row 7, and I see that maximum, exactly what we saw in the graph on the previous slide. And then the next thing down, it tells me the elimination half-life. And so I see the half-life for both of these. So again, exactly what we saw on that curve. And then if you go down further, this next table has a whole list of half-lives for different populations. And so this one is adult populations, elderly, and populations with different challenges. And so what do we know about the drug? We know the half-life. And so we can use exponential models, specifically a half-life model, to figure out how much would remain in a patient at different times after they had been given a dosage of Rocephin. So then we get to our pre-lecture notes. And the first thing we had to learn about in pre-lecture is this number E. So we had seen E at the beginning of the course when we were doing some financial calculations, and we found that E is a button on our calculator. E was discovered by Leonard Euler, and many people accused him of naming it E after himself. He claimed that wasn't the case, but you decide what you want. He claimed that A, B, and C were used in the Pythagorean theorem, D was distance, and E was the next available letter. So E is approximately 2.718282, and it continues for there because it is an irrational number, which means the decimal continues forever. You do not need to memorize the decimal or the approximation of it because you're going to always use that on your calculator. We're going to use E whenever we have that keyword continuous, so continuous growth or continuous decay. When we look at a formula, as we have at the bottom of our screen here, the A value is the initial value. And then the E replaces what we had in this past week as 1 plus R, that part in the parentheses, which forms the base for our exponent. The exponent here is where you're going to put the decay or growth rate, and you are going to change that rate to a decimal just like you did before. And you also include the t, the time elapsed, as part of the exponent, just like you did this past week. So how do you tell if it is growth or decay? Well, if it is a growth model, you are going to have an R value that is greater than 0, so a positive value for R. And if it is a decay model, you are going to have an R value that is less than 0. So when you look at your problem, you will see a negative in the exponent. Let's take a look at an actual example. So you had a chance to read this as part of your pre-lecture assignment. And in this scenario, the 100 is the initial or starting value. When I look at the exponent, it has a negative, so I know it is a decay rate. In the word problem, I see that word continuous, so the base of E is used. I also see that the rate is given as a percentage, and then that is changed to a decimal for the problem. The 3 in the equation comes from the time elapsed, which is the 3 days in the word problem. The next section of our pre-lecture notes gives us 4 different models. Key in this section is that you do not need to memorize. You may use them right out of your pre-lecture all of this week, and when it gets to that final mini test, we will be given the models, so don't memorize. So our first model here is our continuous model, so if you have a highlighter, highlight that in your notes. The letters will be pretty much the same every single model. So P of T is always the population at a specific time. It works instead of the Y variable. And if you want to use Desmos to solve, you should be typing Y instead of P of T. The P with the subscript 0 is also the population, but it's when time is 0, so it is considered the starting population. E is that base, that irrational number that is used for both continuous growth and decay. R is the growth or decay percent as a decimal, and so that carries over from this past week where R was the percent as the decimal. And again, T is time. Our next model is called the doubling time model, so you may want to highlight that. And the base in this model is 2, because if you're going to double something, you're going to multiply it by 2. Again, do not memorize. You're always going to be given the model. The letters have the same meaning, so P of t is the population at some time, and Desmos will want you to use that as the y variable. P0 is the starting population, t is time. The new thing is d. D is also a length of time, and it is specifically the time to double. And so you can think of D for double and remember to put the doubling time in that position. Our next model is one that we use a lot in healthcare because it is the half-life model, and most meds give us a half-life. So highlight half-life, and we have the 0.5 in the middle here, which is the percentage for half, and so that's why they go together. The letters are the same. Here, the D, again, is a length of time, just like D was in the previous model, and specifically, it is the time to decrease by half, or you could think of D as the half-life. Our final model is a version of the model that we used this past week. Instead of having X and Y, it does have the P of t. And so the P of t, the population, the start, the R, again, is the percent as a decimal, and that you could use a positive or negative here, depending if it is going to grow or decay. You want to use this model, so highlight your model, here your equation, and then you want to use this when you know the percent for 1 unit of time. And so it is used a little differently than the continuous model, even though that wording would be very, very similar. So from here, we are going to go into trying this out with some actual problems, but this video is just a run through of those opening notes, giving you a chance to check your pre-lecture notes and make sure you have the correct information that you need.